All right, so we're going to start chapter 6 now. And chapter 6 or 6.1 will include perpendicular and angle bisectors. The first thing that you need to know is what a perpendicular bisector is and what you can actually perpendicularly bisect. So what you can take the perpendicular bisector of is just a segment. But a perpendicular bisector could be a line, it could be a segment, or it could be a ray. Cuts a segment into two congruent parts. So it actually goes through the midpoint. Here's my segment AB. If I have the midpoint, the perpendicular bisector has to go through that. And let's just say this is point M, and it has to be perpendicular as well. So to show that, if I say line L is the perpendicular bisector of segment AB, goes through the midpoint, which means it cuts it into two congruent parts and it's perpendicular to it. That's why it's called the perpendicular bisector. And then the other term that you need to know is equidistant. Equa meaning equal, and then distance meaning distance. So if something's equidistant from two things if it's the same distance away from those two items. Since you all live in Lake Stevens, or most of you do, let's just say, even though maybe it's not the case, that LSMS is equidistant from Caballero and the Tom Thumb grocery store. So what that means is LSMS is the same distance away from Caballero as it is from Tom Thumb grocery store. So that's the definition of equidistant. So talking about perpendicular bisectors, I have line L here, the perpendicular bisector of segment AB. And then what the perpendicular bisector theorem states is if you have a point on the perpendicular bisector of a segment, so I'm just going to call this point C. I could have put point C here, 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 anywhere on that. But C, if it's on the perpendicular bisector of AB, is equidistant from the endpoints of that segment. So C is the same distance away from A as it is from B. So those two distances, CA and CB, are the same. And then I just wrote out exactly what the perpendicular bisector theorem states. Notice, so here's a little bit of review for you. The perpendicular bisector theorem is written as a conditional statement. So theorem 6.2 is actually the converse of that. Before I write it out, maybe just pause the video here and then see if in your notes you can write the converse of the perpendicular bisector theorem. So the converse of the perpendicular bisector theorem states if a point is equidistant from the endpoints of a segment, then it has to be on the perpendicular bisector of the segment. So let me give you an example. Let me zoom out a little bit so we could see a little bit more of the diagram that I'm about to draw. So let's just say I have a segment PQ. If a point is equidistant from the endpoints P and Q, right here, let's just call this point T. If it's the same distance away from P as it is from Q, then it has to be on the perpendicular bisector of the segment. And you might say, well, can't the point that's equidistant from the endpoints be on the segment itself? Yeah, point T or whatever you want to call it, point L or whatnot. If that's on the segment, it's still on the perpendicular bisector, even though it's the midpoint of the segment as well. But that's the converse of the perpendicular bisector theorem.